So here we are, we're on the third and final part of the first lesson from chapter 11. And what I'd like to do with you to conclude is go through an example of a significance test that employs the T procedures. And easier said than done. There we go. Okay. So here's a situation. This comes out of the book. It's an example in the book. You got a cola maker. And what they want to know, or what the cola maker wants to know, is there sweetness loss occurring from the time that a cola is produced to the time when it's actually consumed? And so here's what the cola maker does. It hires trained testers. We're going to assume that that it's a well-designed experiment. And these trained testers will test the sweetness of the soda. They'll say, you know, this is a level 5 or a level 6 or a level 8. And then they store it for months. And then they pull it out again, and the same trained testers will now once again measure the sweetness of the soda. And so you have a measurement before and a measurement after. What we're going to look at in this problem is the difference between those. So you can imagine any piece of data that we have as being the sweetness level before, and then the sweetness level after storage being subtracted from that. And here's what our data looks like. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you'd like to pause for a moment, you can pause so that you can get all of that data into your calculator. Here's the question. Is this data good evidence of sweetness loss? So that's a significance test. Let's assume that we're dealing with a 0.05 significance level. Okay. So same questions we've been practicing. So you can think of this as a dry run, at least at this level for the test that you're going to take on Friday. And so our population is going to be as specific as we can. We don't just want to say cola. We want to say it is sweetness level differences. Okay, and then our parameter of interest is going to be the mean difference. So we have a null hypothesis. Remember, the null hypothesis is always something that is easily testable. And in this case, it's going to be that the mean difference is 0. And that refers to there being no loss. Equal sign always means it's easy to test. Now, the alternative hypothesis is, yeah, not only do we think there's a difference, but we've got a particular direction. We think that there is going to be sweetness loss. And if there's loss, then the before is going to have a higher score than the after. And since the statistic or the data are collected by doing before minus after, this is going to be greater than 0. First thing to note, we don't know sigma. That means we need to use the one sample T procedure. Okay, is it an SRS? Well, it's not an SRS, but we'll assume it's a well-defined experiment. Is it normal? I checked the normal probability plot, and it was linear enough, so we're good to go there. So now let's calculate the test statistic, and we're working with what you see up here in the corner. The T is equal to x bar minus mu over blah, blah, blah. And so x bar for the difference, this I'm getting out of one variable statistics, is 1.02. And the sample standard deviation is 1.196. The number of samples is 10, And that means that our degrees of freedom is not going to be 10. It's going to be 1 less than 10, which is 9. Therefore, our test statistic, our t, is going to be our mean, or our sample mean, minus our mu, or our population mean. Now, we're assuming under the preposition of the null hypothesis that that is 0, divided by S over the square root of, and here you want to use the sample size, so that's 10, and we come up with that being equal to 2.70. And keep in mind that the degrees of freedom are 10. So in order to find the probability that's associated with that, which is what we want the p-value. And the p-value is equal to the probability that t is actually larger than this 2.70 by a chance alone. What we need to do is go to the table. Now on the table, you're not going to get an exact value, and here's why. We're only given these percents up here at the top. So we've got 9 degrees of freedom. That's right here. I'm going to highlight that row. And we just want to move along it until we get close to 2.7. So it's less than 0.1. It's less than 0.05. It's less than 0.025. But it's bigger than 0.01, but not by much. This is 2.8. We're looking for 2.7. So between 0.025 and 0.01. For our purposes, that's enough for us to conclude that since this p-value here is smaller than 0.025, we are going to reject. Now, if we wanted to get it exact, we could. Here's what you do. Grab your calculator. And in your calculator, input, first go to distribution. And there should be something that says TCDF. I want you to choose that. It works almost exactly the same as the T, or as the normal CDF. You put in the range of scores, so from 2.7 to infinity, which we're calling E99. And the one other piece of information you have to tell the calculator is what kind of a distribution it is. So we know it's a t distribution, but how many degrees of freedom? So you would also put in 9 degrees of freedom, and what's going to pop out is it's almost exactly 0.01. So there we actually can get the p-value. Last step, interpret the p-value. We reject the hypothesis that there is no sweetness loss at the 0.05 significance level. We accept the hypothesis that there is sweetness loss. So there it is, kids. Next time you're buying a soda, check the expiration date on it. Here's your assignment. We covered this. You're going to need to read those pages. And then the first problem set in Chapter 11 is to do these 1, 2, 3, 4, 5 problems. They are due on Friday, but I want you to start them now.